So it's really a great pleasure to have Eric here. I've known Eric for a few years from T2K mostly and GU. Eric did his PhD at Chicago University on kaon physics. And after that, he moved to neutrinos, postdoc at Columbia, working on NuTev and mini-boon. And then he moved to the University of Colorado at Boulder, where he's been since and is now a full professor. And so after mini-boon, Eric's worked on T2K, where he built the magnetic horns that focus the neutrino beams. And he's also been leading the NA61 experiment for a while, and he's, as of this year, spokesperson of the experiment. So I think that's the brief introduction. Eric, please take it away.
Okay, is there a pointer I can use?
I'll get it.
Okay, thanks. Okay, well, I'm certainly glad to be here and glad to talk about the physics of neutrino flux and what we're doing on NA61. So I'll go through what neutrino beam physics is and talk about the NA61 neutrino program, some new-ish results, and the data sets we have recently reported and what's upcoming and new opportunities we have over the next several years. All right, so modern long baseline neutrino oscillation experiments use what we call conventional beams. Primary protons here strike a target. Secondary mesons are produced in that target. They're focused by magnetic fields, and then they enter a decay region, and the decay of flight to neutrinos upstream of the beamstop. And of course, the neutrinos continue through the beamstop. All these types of beams tend to have common properties. They're predominantly nu-mu, with nu-e contamination at the roughly 1% level from muon and kaon decays. If you change the polarity of the horns, you can get a nu-mu bar beam with also, of course, with some neutrino contamination. Even what are called narrowband beams, they tend to have tails to higher energy. And the fluxes all have significant systematic errors. Yes?
Can you share the screen?
Oh, I'm not sharing the screen. I'm sorry. Ah, here we go. Okay. So the target has to be about 2 interaction lengths in the beam direction. And this is, of course, to maximize interactions. It should be wide enough to contain the primary beam, but it's got to be narrow enough to allow interaction products of a typical transverse momentum to escape the side. The target material, generally you want to be low atomic number because lighter nuclides tend to produce shorter lived radioactive isotopes, which means that when your target is done, you can store it without enormous amounts of shielding around it, only large amounts of shielding around it. And if you want to maximize interactions while minimizing multiple scatter, then you want a low interaction length to radiation length ratio, and that will also tend to get you toward, in this case, lower Z materials. Targets have to handle a very high beam power deposition at the 100 kilowatt level for Dune coming up. Modern targets need dedicated cooling, and future targets may not even be able to be solid. We're not quite at that point yet with the next generation. So neutrino beams use horns for focusing the mesons coming out of the target. Horns are a very old idea. It's basically 2 coaxial conductors. You have an inner conductor, and the current goes down the inner conductor. The current comes back out the outer conductor. And so you have a toroidal magnetic field in between those conductors. And this means that if you have a positively focused particle that's diverging and enters the field region between the conductors, it'll be focused forward. If you have a negatively charged particle, it will be defocused. And of course, if you reverse the horn polarity, you get the opposite sign focusing. So the inner conductor has to be thin enough here so that most pions can pass through, because remember, they're produced out here, or sometimes even here, and they have to get through the wall into the field region. So this means that you need to have the inner conductors be in the few millimeter range, not much bigger, or you start to get significant pion loss in the inner conductors, which defeats the purpose of having the horn. But Conductor currents also have to be in the hundreds of kiloamps range, so water cooling and pulse operation are necessary, otherwise the horn will fail immediately. And generally, horns are made out of aluminum alloy. So a single horn generally reduces the angular spread of the beam by roughly a factor of 2, depending on how you count. And what you get out of there, if you look far enough away, it starts to look like a point source of mesons again. So you can then improve the focusing by adding additional horns downstream. So if here's your first horn, you have overfocused particles, they cross the center line, then they get corrected. If you have underfocused particles, they continue diverging and get corrected. If you have well-focused particles, you avoid putting any extra magnetic field there. So you are able to improve the spread of phase space by a reasonable factor with each additional horn you add. So it's common for beams to be designed with 2 or 3 horns in series. This is what these things actually look like. This is what the 1960s version looked like at CERN. This is what the 2010s and current version looks like. This is what's used at JPark. This is horn 2 being built in our shop, at our university. Okay, so the flux of neutrinos comes from meson decay. So the proton beam enters the target, and of course you have primary interactions in the target, which produce mesons, which get focused in the horns, decay to neutrinos. That is a dominant, but not greatly dominant source of neutrinos in the beam. Another source is pions or hadrons that reinteract in the target and produce new mesons in the target. Then those get focused. But the horns themselves contain a substantial amount of material. And so a lot of at the 10% level in most beams, actually, a lot of your mesons that decay to neutrinos in the detector are actually produced outside of the target in other material around. So all of these contribute significantly to the neutrino flux. Now, we generally use Monte Carlo techniques to simulate the beam, but it's a really challenging, complicated environment for Monte Carlos. And with standard simulation tools, uncertainties can be very large, 20 to 50%, even 100% for chaotic decay neutrinos. The Monte Carlo has to simulate the interaction of the proton in the target, the production of pions and kaons in that interaction, propagation of those particles through the horn, through scattering interactions and magnetic field, propagation through the decay volumes, losses in the beam absorber, and the meson decays finally to the neutrinos and muons. And except for this last one, all of these require knowing hadron interaction physics. So what hadron interaction physics do we have? We have at all of the major labs and all the major beam lines that are happening now or will happen soon, the primary particles, of course, are protons, and in most cases, the targets are carbon. One exception is the booster neutrino beam, which is rather lower energy and uses a beryllium target. But T2K uses 31 GeV, NUMI uses 120 GeV, and LV at FDUN will use somewhere between 60 and 120, almost certainly 120. So we use 2 complementary techniques to understand the beam well enough to do oscillation measurements. One, of course, is a near neutrino detector. This is really critical. The goal here is cancellation of flux uncertainties in the near-far ratio. Of course, it's not perfect for constraining the flux for several reasons. Neutrino cross-sections, of course, don't cancel if the detector materials are different, as is the case in T2K. But even if the detectors are the same, there are parallel effects, parallax effects due to being near an extended neutrino source. And if you don't understand your flux, you can have biases on your reconstruction parameters as well. So the other technique then is measurement of the pion and kaon production and interactions directly. So this, of course, is essential for measuring neutrino interaction cross-sections because there's nothing that cancels there. And it also will reduce oscillation systematic errors. So we use generators, including Fluka and J4, with various physics lists. This is a comparison of the pi to mu flux in the NUMI beam with different physics lists in J4. And you can see there are significant differences among the physics lists. And so we want to have more constraints on these hadronic processes. So if you look in the literature for external measurements of meson production, you find things like this. These are fits to multiple measurements at different labs with different beam energies. These measurements were made many, many years ago, in some cases going back to the late 1970s, for other purposes with very different types of detectors, a lot of bubble chamber data out there. And with these very different kinds of experiments, and also very old results from when analysis reporting styles were different, it's very difficult to combine systematic errors across them. So there's also then a lot of model dependence in extrapolating from different energies and target nuclei to what you actually want. You can see none of these energies is actually the energy of any neutrino beam proton source. So the answer then is to do dedicated experiments for this. And in recent years, there's been sort of a loose program of measurements specifically for neutrino experiments. This began about 20 years ago with a HARP experiment, and now emphatic and NA61 shine at CERN are the current generation. So NA61 is a fixed target experiment using the H2 beam at the CERN SPS. People who work on Proto-Dune will recognize that as the same beam that feeds the vertical drift module. The spokespersons are Severin Kowalski from the University of Silesia and myself. It's designed around the former NA49 heavy ion spectrometer. And the primary proton beam comes from the CERN SPS, but we use a secondary beam which can give us a wide variety of energies. Here's the collaboration at a recent meeting. It's a very diverse physics program in NA61 because it's not all or even primarily neutrino physics. There's a large strong interactions heavy ion physics program looking at the onset of QCD confinement, search for the critical points, and open charm production. That's a major current physics program at NA61. Also, cosmic ray interaction studies, including deuteron and anti-deuteron production in the galaxy, and nuclear fragmentation cross sections. We just took data a couple of weeks ago on nuclear fragmentation. And finally, hadron production for neutrino beams. So this is a general overview of NA61 as it evolved from NA49. And NA61, we have detailed beam instrumentation, several large acceptance TPCs, 2 superconducting analysis magnets, time of flight detectors, a forward hadron calorimeter. So I can go through these one by one. So upstream of the target, we have scintillators that serve as the initial trigger detector timing signal. They veto halo particles also. Then we have a couple of particle ID detectors in the beamline. One of them is called a CEDAR. This is a standard device that uses a Cherenkov ring to identify particles. It's actually a very clever detector. It uses a series of mirrors and 8 phototubes that focuses the Cherenkov ring on these 8 phototubes. So if the Cherenkov ring is the right radius, all 8 phototubes will fire in coincidence. Also a threshold Cherenkov detector can be used, so we can really get very high accuracy in identifying our beam particles. Then we have a series, and I'm sorry, these everything that's sort of reddish is really hard to see on this projector, I'm afraid. I guess that helps a bit. Beam position detectors are MWPC-based tracking detectors that measure the transverse position of each beam particle. For the heavy ion physics, we use silicon BPDs now. And there's an additional scintillator downstream of the target and downstream of the first of the superconducting dipole analysis magnets, we call S4. This can veto forward particles at the beam moment. And so the reason we use this is we want to trigger on interactions in our target. And so if there was no interaction in the target, then you just get a beam particle sailing through, and that fires S4. So we veto events with S4 firing. And then we have, in these blue boxes here, are all large acceptance TPCs that provide charged particle tracking and measure DEDX. So these first two, these Vertex TPC 1 and 2, sit inside superconducting analysis diodes. Then downstream of the main TPCs, we have time of flight detectors. They are scintillator, and more recently, some of the time of flight detectors have been replaced with a multi-layer RPC time of flight detector. And finally, what we call a projectile spectator detector, which is sort of nuclear physics jargon for a forward hadron calendar. And generally, this isn't used much for neutrino measurement, so I'm not going to follow up on that. So this is the kind of particle identification quality we could get out of our detector in the few GeV range where we really do the best. This is DDX versus momentum. You can see the pion, kaon, proton, and deuteron curves here, and of course they do cross one another at certain energies. And then at the lower energies, we also have very good time of flight. Lower momentum, we also have very good time of flight separation as well. So if we use them both, we get very nicely separated particles in the few GeV range. At higher momentum, we basically have to depend on DEDX, and we still do pretty well over a large part of the range. So there's been a multi-phase program ever since NA61 started on hadron production measurements for neutrino physics. There have been major upgrades during each of these long shutdowns, and the plans are continuing to evolve for future upgrades and operations. So we do two approaches in NA61 for neutrino physics. We do thin target and replica target measurements. So if you want physics cross sections to go into the models for generating hadronic interactions, you need thin target measurements. So this measures the physics cross section, total inelastic and production cross sections, and differential spectra to be used as inputs to these generators. But we also need measurements on replicas of the actual targets that are used in these experiments, because these measure both beam survival probability and differential yields. They make measurements that are specifically for each neutrino beam, and we typically use results from these to reweight the particles in the beam Monte Carlo at the surface of the target. So these are some of the replica targets we use. This is a thin target, graphite target. This is the T decay replica target. This is the NUMI Nova replica target. These are all these. It doesn't look like it, but these two are actually in the same place in front of our spectrometer. So we started off doing measurements for T decay, and that has produced 8 publications on thin target and replica target measurements. This is one of the measurements that we did. This is just proton carbon 30 GeV, proton carbon. This is the thin target result. This is just one angular bin shown here. This is 20 to 40 milliradians, pions, kaons, and protons. You can see that especially for kaons and protons, the Monte Carlo generators failed badly. This is not a surprise. And this was published in 2016, along with yields of negative particles and neutral strange particles. Well, replica target measurements. As I said, this is using the exact target geometry of a particular neutrino beam. Most events do have primary and secondary interactions in the target. So we measure the yields versus not only P and theta, but also the Z position along the target, and possibly for targets like NUMIs that aren't cylindrarly symmetric, the azimuthal angle as well. And we measure the beam particle survival as an additional constraint on the production cross-section. I already mentioned that we use this to apply weights at the surface of the target in the neutrino beam simulations. So these are the full differential yields from the T decay replica target. The longitudinal position along the target is binned into 6 bins. 5 of them are bins along the side of the target, And the final one, 6, is particles that escape out the downstream end of the target. So this is Z1, 2, 3, 4, 5, and 6 here for a particular angle bin, ion yields from 60 to 80 milliradians. So this just gives you a sense. And we have, of course, a full spectrum of angular bins as well, and other particle yields. So this is the result on the T decay flux prediction. This is the fractional systematic uncertainty on the T decay flux as a function of neutrino energy. And I'm not even showing a result, a prediction here with no NA61 result. That has never actually been even been released, but the uncertainty would be extremely high. But from each of our data sets, starting with the thin target here in the dotted line, then the first dashed line here is the low statistics replica target measurement, then the high statistics replica target measurement. You can see that the systematic error on the flux has been going down with each new data set from NA61. Okay, so that was the initial T decay phase. So in run 2, we did a second phase of NA61 neutrino measurements, mostly motivated by the NUMMI and DUNE beamlines at Fermilab. But this made specific upgrades, a forward tracking system. This is one of the chambers being, this is the field gauge of one of the chambers being put together. A new tandem TPC concept that was used for this for rejecting out-of-time tracks. I'll talk about that a little later. New readout electronics were added for the time of flight detector. And the data set, as I said, was collected the second half of the last decade. So this is the NA61 setup before 2017. So you can see there was a hole, except for the gap TPC, there was a hole right down the beam line. So forward particles, we actually had 0 acceptance for. This is because the heavy ion experiment has an intense beam with very high multiplicity of interaction products. So we really wanted to minimize material here for the heavy ion running. But for the neutrino running, we really want to have tracking in the forward direction because forward particles are very important for neutrino physics. So we built these new TPCs for the neutrino program. They were designed to have a very low material budget compared to the older TPCs, with a light plastic frame, a thin printed Kapton field gauge. And the first of these FTPCs can be removed from the beam for heavy ion running. It uses the same electronics as the other TPCs, and because there are, even in the neutrino running, there can be high rates in the beam region, we developed this new tandem TPC concept. So for successive, so if you have a TPC, you have an in-time track, it's good track, you reconstruct properly. If you have an out-of-time track, it's indistinguishable from an in-time track, but shifted in the drift direction, apparently shifted in the drift direction. So what we do is we have 2 successive TPC volumes with the drift in opposite directions. So if you have an in-time track, you'll get a nice continuous track. If you have an out-of-time track, it's going to be shifted different directions in successive field volumes, and so you'll get a disconnected track that won't be reconstructed. So we wrote a paper on this in GINST a couple of years ago, and generally this approach has been working really well. Here's an event display for a 120 GeV proton carbon event. So you can see tracks in the vertex TPCs here. They're curved because of the magnet. The gap TPC and forward TPCs 1, 2, and 3 are shown here. And actually, forward TPC, this is actually 2 separate tracks in the TPCs. So here are the first results from this program. This is total production cross sections on nuclear targets for pion and kaon scattering as well as proton. And this is done for data without the magnetic field on. That's the best way to measure the total cross section. And our definitions here, just if you get into these, you really get frustrated with the definitions of the production, elastic, inelastic cross sections. because they're not always handled consistently. What we call the production cross-section requires new hadrons to be produced. So we take the total cross-section, we subtract the elastic, and we subtract the quasi-elastic, where the nucleus is broken up, but you have no new hadrons produced. So before this, NUMMI had roughly 5% error on pion interactions, 10 to 30% for kaons, and had to extrapolate from other energies from protons. So we've already, you can see the suppressed zero on this, we've already improved the errors considerably for that, just with this first result. And then from 2016 and 2017, we took a whole lot of different data sets with different beams and different target species. The goal with these is really to span the phase space of primary and secondary interactions and neutrino targets and surrounding material. So each of these measurements basically becomes a point for interpolation in Monte Carlo generators. And you can see most of these have now been published. Here's an example. This is the pion carbon at 60 GeV data. These are differential production yields for positively charged particles. Of course, we also have negatively charged particles. This is one of the ways we analyze the decay in flight using V0 reconstructions, using neutral particle reconstruction from the decay vertex. We can visualize the events using what we call Armenteros-Podolansky plots here from in PT versus momentum asymmetry of the tracks. So particle-antiparticle decays, like pi plus, pi minus, show up in this centered curve, and the baryon anti-baryon decays show up as displaced curves here. So from our thin target proton carbon 120 GeV data set, this is the highest priority data set we have in our other than replica target data, because this is the primary proton interaction in NUMMI, NOVA, Minerva, almost certainly for Dune as well. This relies on these new forward TPCs, you can see here, to provide the forward acceptance. And the new tracking algorithm was developed for integrating the FTPCs into this analysis. It's a cellular automaton-based local tracking with a Kalman filter for the global track fit. And we had about 3 million interactions. And remember that number, 3 million interactions, for what I'm going to tell you about our next runs. These are some K-short and variant mass fits from 2016 and 2017. The signal to background ratio looks rather different because in 2016, we had a higher magnetic field and no forward TPCs. In 2017, we had a lower magnetic field with a full forward TPC system. So we're trading off resolution for forward acceptance here. And our results combine these two data sets. These are lambda and anti-lambda reconstructions. So I can show you that. Once again, we have the 2017 data with a lower resolution, but a better forward acceptance. So these are our neutral particle spectrum, our neutral particle yield results. We're getting roughly 15-ish% errors on these neutral particles. The charged particles, we have somewhat better results because, of course, we have much higher statistics on the charged particles. This is the 5 to 10 milliradian bin here. These are pi plus proton, pi minus, anti-proton, pi plus, and proton spectra. Once again, with the 2016 and 2017 data sets combined here. So those are that's 120 GeV, that's the primary proton beam energy for the neutrino beams. But we really want to do intermediate energy interactions as well. So this is because, as I say, the energies below the primary proton beam energies provide constraints for models to predict the secondary interactions. And NA61 took data with 90 and 60 GeV protons. The 90 GeV analysis is finished. It was submitted to PRD in October. It's in the publication process now. The 60 GeV analysis is at an advanced stage. So here's the 90 GeV. This is our newest result. This is once again the neutral particle invariant mass reconstructions. Here are some of our results for charged particle yields. Here you get a sense of the kinematic binning that we're able to use. So this is angle theta versus momentum. So this is yield versus theta and momentum for each of these particles. You can see there are some, it's a little hard to see, but you can see there are some stripes with zero yield up there. Those are regions we cut out because the DEDX yield crossover for different particle types at those momenta, so we're not able to have any sensitivity there. So next I'm going to show you one-dimensional spectra for a specific angle bin. This one here between about 20 and 30 milliradians. So this is the pi minus result in the 20 to 30 milliradian bin. From this, we're getting 5-ish% uncertainties on pi minus. These are the pi plus, which gives similar results, similar sensitivity to pi minus, k plus and k minus, proton and k short, where we don't have as good errors. So how do we actually use this to get the results into the neutrino simulation? For the Fermilab experiments, there's a software product called PPFX, which is Packaged to Predict the Flux. This was developed by the Minerva collaboration for NUMMI. It's basically being used for DUNE as well. This is an experiment-independent neutrino flux determination package, and it was the subject of Leo Aliaga's PhD thesis a few years ago. And this provides hadron production corrections and propagates uncertainties using external hadron production data. So these are the processes that are included in PPFX. Everything that's in red is what's going to be improved by the NA61 proton carbon results. NA61, adding NA61 results is almost completed here. So there'll be a new PPFX release quite soon with improved results from NA61. This is the current PPFX uncertainty without NA61. And that's making some possibly dubious assumptions about momentum scaling. So I'm actually not sure the errors really should be that low. So we took data on a replica of the NUMMI target a few years ago. This is the NUMMI target in the NA61 beam. The NUMMI target has a very exotic geometry. It is not a cylinder. It's produced with these fins, most of which are horizontal, but one is vertical. And the beam actually just skims the top of this target. So it's very non-azimuthally symmetric, which adds complication for us. The calibrations are still in progress on this data set. I hope we get results pretty soon. This is the Monte Carlo model of the target. This is what the beam looks like at the upstream and downstream end of the target. You'll notice that the vertical and horizontal scales here are very different. The beam is actually not very broad compared to its height, but we cover the whole region where the proton beam actually hits the NUMMI target pretty well. Okay, so in the last long shutdown, we made a lot of big detector upgrades. And there are two of them I want to highlight because they're particularly important for the neutrino results. One of them is the replacement of the old TPC electronics with a new system from Alice. And the other is a new trigger in DAQ. And combining these two upgrades, that gives us a data collection rate that is now over an order of magnitude faster than we could do before. So I told you about these 3 million and 10 million event data sets. In 2022, we took our first physics data on a new replica of the T2K target, and we got 180 million events. And this is going to give us enough statistics to reliably measure the high momentum kaon yields, which dominate the high energy tail of the T2K neutrino flux. We've also done kaon scattering with thin targets for secondary interaction modeling. And we also took higher statistics, really because we fulfilled our goals a week before the end of the run with the kaons. And so we decided to go back and take some more proton carbon at 120, because once again, that's really important. And we got 20 times our entire 2016 and 2017 data set in a few days of running. And we did it with two different we did it with two different targets, actually, titanium, because there are some titanium elements in this as well as carbon. So the next step this year was to take data with a prototype of the LBNF Doom target. So here's the prototype. This target is the longest target we've ever used in NA61. It's 1.5 meters long. It was designed and built by the Rutherford Lab Targetry Group to the expected dimensions, which are, the design is quite well advanced. So we're pretty confident this will be the dimensions of the LBNF Doom target. So we took 250 million events in this summer of this year. We're also going to plan to run with another version of this target, the sustained geometry that has a lower graphite density, because we're not really sure exactly what graphite material is going to end up being used for Doom. So we're going to do that next year. Here you can see the target installed. You can see the target being aligned. In order to do this, we added a new detector to our system, which is a new TPC that sits immediately downstream of the target. The reason we're doing this is because in the T2K replica target analysis, a leading systematic error was the backward extrapolation of shallow angle tracks from the detectors to the target. So if you have your detector here and you're extrapolating back to the target, it doesn't take much of an angular error. It doesn't take much of an angle reconstruction error to move this intersection point into the wrong longitudinal bit. So this is really a big problem for the T2K analysis. So and for the Dune analysis with this 1.5 meter long target and a higher energy primary beam, it would be a much worse problem. So we added a new TPC that was built this year. And here you can see a very high resolution, a very high multiplicity event in that TPC. This was built by the KFKI Victor Group in Budapest. And this sits just downstream of the target, basically to measure, only dedicated to measure the exit point of the tracks from a long target. After next year, we're exploring having a low energy beamline built for NA61. Right now, we can go down to 20-ish GeV reliably with protons in our beamline. But there's a lot of groups interested in hadron production with beams in the 1 to 20 GeV range, which is below the range where this the current beam can really provide reliable beam. Probably the most exciting thing here that we can do is we can make a huge improvement to the prediction for the atmospheric neutrino flux. So this is, the longest baseline terrestrial neutrino oscillation measurement you can do. And right now, the flux uncertainties are close to the 10% level. But if we get good measurements with a low energy beam, in principle, we could reduce the neutrino flux errors by factors of 2 to 3. T2K and hyper-K, wrong sign neutrinos are going to become a problem when they get into high statistics, when they get into high statistics data sets in the future. Wrong sign means neutrinos in your antineutrino beam or antineutrinos in your neutrino beam. A lot of these come from neutral kaon decays because those don't get focused or defocused. So they are So they are able to really increase your uncertainties for wrong sign contamination. Wrong sign contamination, of course, is a big problem for CP violation experiments. And then finally, the short baseline neutrino detector at Fermilab depends on a result from the HART experiment from the late 2000s that has significant uncertainties due to what I understand are some inconsistency in the actual data set. So the SBND experiment has quite large flux errors. We could, in principle, reduce those dramatically with an HEEV proton beryllium data set. So CERN has designed a new tertiary branch of the beamline. It's still a secondary beam. It's a tertiary branch, this has been done in close collaboration with the detector. And the goal is really to have beam available after the next long shutdown. It would be great to have it available before the long shutdown, especially for the short baseline neutrino program. That seems to be a heavy lift at CERN right now. So I think we're really not expecting to have this before the long shutdown coming up. So anyone who is interested in low energy data at NA61 or other possible new beam target combinations, the current beam will continue to be available. We'll be able to switch between the low energy beam and the beam we use now. There was a workshop held about 2 years ago on physics opportunities at NA61 beyond the next long shutdown. We are, of course, looking for new ideas, and we're always looking for new people to work on this. We are absolutely person limited in this experiment, like everybody else, of course. But these are some of the potential new physics topics and experiments that we can improve. Okay, so that's all I have. NA61 has really provided unique and critical data to support the global neutrino program. These efforts have reduced T decays flux errors by a very large factor. There are new analyses coming out now geared toward the current Fermilab program. More are coming in the next couple of years with both the T decay and the LBNF dune targets. And we're studying a low energy beam and other future options. Thanks.
Right, Barry?